Hello everyone, I'm Hanyan from Biomedical Engineering and my PI is George McConnell, and today I'm going to show our technique for DBS targeting, which we call spacer. So one clip I want to show, DBS is actually a treatment for Parkinson's, and as you can see, the DBS is on the tremor got improved from this Parkinson patients. So currently there's 10 million patients living, suffering with the symptoms, and the $6 billion of market, and there's 2 billions are DBS. So what is DBS? It's actually a implantation that have a neurostimulator that implanted in the chest, and there's a wire that connect to an electrode, and the electrode is implanted in the brain, and the tip of the electrode has to be implanted precisely in a brain target to make it work. So as I just said, the key to this treatment is to implant the electrode to the precisely target. So currently the doctors are using imagings to do the targeting. Basically they do a pre-operative imaging. They have a original coordinates and they put the electrode in, and they take another imaging after. If the electrode is not implanted at the coordinates that planted, they have to take it out and put it in right after, so for several times. So I actually went to OR with the doctor. That day, the whole targeting process took 5 hours and about 7 passes of imagings. And just keep in mind that the brain surgery is actually the patients have to be keep awake. So just imagine how long for them the targeting is. So as the engineer, we developed a more quantitative way to target. So basically, instead of relying on imaging, we rely on electrophysiology. As the doctors lower the electrode gonna send the brain signals, and we would know, we do data processing, and then we would know where the electrode went. So a little preclinical studies I did, this is a rat brain, and as you can see, those rat tracks are where I implanted the electrodes. And let's take a look at track 3 and 4. As you can see, those are in different brain targets, and the spacer gonna generate the 2 color maps that are, as you lower the electrode, you could see where you go as the color map. This one track took about 1 minute, so we were hoping that instead of 5 hours, we could shorten it to a very first set of imaging for original coordinates, and then do 1 pass using spacer, and that's gonna be 1 hour top. So we're filing the patenting, and we have a clinical collaboration coming, and there's at the same time I contact 2 companies, FHC and Alpha Omega, and this they're going to embed our algorithm to the existing hardware, so they don't need to have any new hardware for it. So I really hope that spacer are going to save time for both doctors and the patients, and also avoid the side effects that by place the electrode precisely. Thank you.
So Hanyan, how accurate this using this the technology?
How accurate? I did 16 trials, and the pattern shows, or 100% are showing that pattern, and we did statistical analysis is 14 out of 16 are showing significant different quantitatively way.
Is there any experience that the electrode will move during longer time, or that you have to reposition it?
This is for targeting. So this is initial targeting. So after their doctor's going to do the final electrode in. So this is not the long-term one.
And once a long-term is inside there, there's not a problem that it will move?
It seems like not, yeah.
Okay.
So with the conventional method, the story is a system, let's say if they had that imaging real time, let's assume that's the case, then they would have been able to target it. So if it was an image driven then it would not be an issue, and that's the reason it takes 5 hours?
They don't do it real time, so they pre-operative imaging and after. So they don't have a real-time electrode passing through imaging to look at. So it has to be 2 sets of imaging, before and after.
All right, excellent.
Oh, thank you
Hanyan.
so much.